All right, today we're going to talk about a landmark paper that honestly taught AI a fundamentally human skill, how to pay attention. We are diving deep into something called graph attention networks, or GATs, and trust me, they completely changed the game for how machines understand complex relationships.
But let's back up. Have you ever wondered how an AI even starts to make sense of something as messy and complicated as a social network, or a biological system, or even just the web of scientific papers? It's all about the connections, right? That underlying graph structure that links everything together.
You see, for years, AI was an absolute rock star when it came to structured, grid-like data. Think about pixels in an image. Everything's neat, orderly. It was the perfect playground for things like convolutional neural networks or CNNs. But the real world? It's messy, it's irregular, it's complex, just like a social network. And that kind of graph data, well, that was a massive, massive challenge for AI.
And this really brings us to the core problem that the entire field was wrestling with back in the mid-2010s.
I mean, while AI was getting incredible at understanding images and text, it was basically stumped by networks. It just didn't have the right tools to learn from all these rich, interconnected structures that, let's be honest, define so much of our world.
The methods people were using, they just weren't cutting it. On one side, you had what are called spectral approaches, and they were powerful, sure, but incredibly rigid. A model you trained on one network was completely useless on another. It was like having a key that only fits one single lock. Then on the other side, you had non-spectral methods. They were a bit more flexible, but they kind of had to cheat by only looking at a few neighbors at a time, and that meant they were always working with an incomplete picture. And this, right here, is where the breakthrough happens. The paper we're looking at introduced a whole new way of thinking, an idea they borrowed from the world of natural language processing. It was time for a lesson in attention.
In the author's own words, the core idea was actually pretty simple, but totally profound. They said, instead of treating all connections as if they're equal, what if a node could learn to attend to its neighbors? What if it could figure out which ones are the most important, all on its own?
It's such a great analogy. Think about it like you're in a conversation. You don't give everyone's opinion the same weight, right? You intuitively pay more attention to the person who's an expert on the topic. Well, GATs give AI the power to do the exact same thing, to let each little point in a network decide for itself which of its neighbors' information is the most relevant.
So how does this actually work under the hood? Well, it's basically a simple three-step dance. First, a node looks around and identifies all of its direct neighbors. Then, here's where the magic happens. It calculates an attention score for each one of them, basically asking, hey, how important are you to me? And finally, it creates a new, updated version of itself by gathering up all that information, but, and this is key, giving more weight to the neighbors with the highest scores.
But they didn't stop there, which is what makes this so cool. To make the whole process even more powerful, the paper introduces what's called multi-head attention. And really, the best way to think about this is like getting a second or third or even fourth opinion before you make a big decision. Each head is its own independent attention calculator, and by running them all at the same time, the model gets a much richer, more stable understanding of the whole network.
Okay, so the theory is super elegant, but does it actually work? This is where we get to the proof. Let's look at the results and what the paper calls the inductive leap.
First up, let's look at what's known as transductive learning. This is kind of like giving the model an open book test, where it gets to see the whole graph during training. And on two classic datasets, Cora and C2SEER, GATs didn't just do well, they actually outperformed the previous champion, the graph convolutional network, setting a brand new state-of-the-art.
But honestly, that was just the warm-up act. The true test, the holy grail of graph learning, was something called inductive learning. Could a model that was trained on one set of graphs generalize its knowledge to a completely new graph it had never seen before? I mean, this was the exact problem that had totally stumped those old spectral methods. And here it is. This is the mic drop moment of the paper. On a really challenging protein-protein interaction dataset, the previous best model, known as GraphSAGE, scored 0.768. The graph attention network? It scored a mind-blowing 0.973. This wasn't just a small improvement. This was a quantum leap forward.
To put a number on it, that's a staggering 20.5% improvement over the best method that existed before. This one result proved, beyond a doubt, that GATs had truly cracked the inductive learning problem for graphs.
And we can actually see the success. What you're looking at is a special kind of chart from the paper that visualizes the data. It shows what the GAT model learned about the scientific papers in that Cora dataset.
and you can see these beautiful, clean clusters forming. Each color is a different research topic. The model figured out how to group all these papers together just by understanding their connections. It's amazing.
So what's been the lasting impact of all this? What's the big takeaway? Well, that brings us to our final section, the GAT legacy. You know, it's hard to overstate the influence of this paper. It didn't just give us a new model. It gave us a whole new building block for the entire field of graph neural networks. This unlocked incredible applications in areas like drug discovery and the recommendation systems you use every day. And maybe its greatest legacy of all was proving that this idea of attention wasn't just some trick for understanding language. It was a fundamental principle for how AI could understand all kinds of complex relationships.
And this leaves us with a really fascinating question for the future. Now that AI can finally, truly understand the intricate web of connections that make up our world, what previously unsolvable problems are finally within our reach?
And that's our look at graph attention networks. Thanks for joining me. As always, this is for entertainment purposes only.